presentation for hands-on session for Xilinx platform. So this is the ISC Design Suite 14.7 from Xilinx platform. So this is the tool we are going to do the FPGA design flow. So I'm clicking this tool now. Now I need to create a project. So go to File, New Project. So just give any project name as training. So training. So just browse the location. So VLSI. So okay. Next, so I need to select the family of FPGA. So if you click on the family, you have a lot of ICs available: Arctics, Automotive, Cool Runner, Kintex 7, Spartron 3, Spartron 6, Vertex, and CPLT. So I'm going to use Spartron 6, and I need to select the device also. So I've taken, so here also you have a lot of options. So I'm choosing XC6XL, X16, and the packages. So this will have 256 input output lines, so which can be programmed as input or output, and the speed grade. So speed grade is -3. So this is the factor which defines the configuration for which rate. Okay, and my default top level source type is HDL. Synthesis tool is inbuilt XST, and simulator is inbuilt simulator. The preferred language, I can select it as VHDL or Verilog. So I'm going to program through Verilog. So I'm selecting as Verilog. Next, finish. So you can find on the left hand side a pop-up menu, so which indicates the device selection. So you just go to right click, go to new source. Now you select this Verilog module. You just provide the name as FA, because I'm going to design a full adder combinational circuit. So the first step is design specification. So the design specification specify what are the components requirement, what are the inputs, and what are its associated boolean expression. So a full adder is a combinational circuit which will have three inputs, A, B, and C in, which will produce two outputs, sum and carry. And the boolean expression for this sum and carry is sum equal to A XOR B XOR C, and C out equal to AB plus BC plus AC. Okay, so the first step is the design specification. So that I'm going to define. Next, I'm going to do the design entry now. So design entry, so whatever the verbal description, I'm going to convert this into an HDL process. So I've specified the file name as FA. Next, now you just define the port. So the ports are sum and cout. Just you click the port name. So port is output port. So these two signals are output ports, and A, B, and Cn are the inputs. Okay, by default the direction will be in input. So three types of ports can be done. One is the input, the other one is input, output. In out is also bidirectional port is also can. Okay, so next, finish. So now I have to write the functional description. So I'm going to write the functional description in terms of data flow modeling. So now assign sum equal to A XOR B XOR C in. Now assign C out is equal to A ampersand B, or is pipeline symbol, A ampersand C in, and pipeline B ampersand C in. So I have given the functional description also. Now I'm going to save the file. So this will be saved as FA now. Now I need to check the whether the syntax and everything is correct. So go to synthesis now. Check for check syntax. Now no errors found. So synthesis. I mean simulation is syntax is completed now. Now I have to check the functional requirement of this FA through a test bench creation. So behavioral check I'm going to perform now. Again, click on the device, right click, new source. Now I will create a Verilog test figure. You just specify a name, FA underscore test. So now next, finish. Now the tests are created. Now I have to initialize the inputs now. So how to initialize? I'm assigning A equal to 1 tick B of 0. A input is 0. Similarly, B input is also 0 and C in input is also 0. Okay, so I'm going to test this case for the next 5 nanoseconds. So hash 5. Now my C in input is going to be 1. So one more input is also I'm going to add. So now both B and C in are 1. One more input I'm going to check. So all inputs are 1, 1, 1. So I have to terminate the simulation hash 20 $stop. So dollar stop. And now you save this test bench. So once this test bench is created, I'm going to check for the device under test. So go to simulation, click on FA test, iSim simulator, behavioral check synthesis. So now we can see the functional simulation. So now this is your functional simulation. Now we will check on the simulation. So this is the cursor. So initially all the inputs are 0, 0, 0, 0. So sum is also 0, C out is also 0. Now C in alone is 1, the remaining two inputs are 0. So expected sum output is 1, C out is 0. Next one, B equal to 0, C in equal to, A equal to 0, B equal to 1, C in equal to 1. So the expected output is sum should be 0 and the C out is 1. So this is also correct now. Now all the inputs are 1. So the expected sum and C out should be 1, 1, 1. Right. So the functional verification is done. So from the FPGA design flow, design aspect, we have completed 3 stages. The first stage is design specification. So as an example, we have taken the design of full adder circuit, and the design specification is so the design it is a combinational circuit which will have inputs A, B, and C in, which have to output sum and Cout. So the functional description of the circuit is sum equal to A XOR B XOR C, C in, and Cout equal to AB plus AC in plus BC in. So the next stage is the design entry. So design entry where HDL conversion will occur. So I have converted the design specification in terms of HDL code, and then I have to go for the functional verification testing. So this is the functional verification testing. So next we will move on to the implementation stage. So now I'm going to do the fourth process of a design flow. So synthesis. So here is the process where your HTL code will be automatically converted into RTL. So the gate level and its corresponding netlist conversion. So I'm clicking this synthesis process now. So in the synthesis process, you can see the synthesis report. So how many number of LUTs, that is lookup table, is used, how many CLBs are used. For this circuit, it is utilized 2, and a number of flip-flop pair is 2, and IOs are 5. 3 for the inputs and 2 for its output. And from the synthesis report also, you can see the combinational path delay. Okay, so the combinational path delay refers how much time the input to output for a particular input to reaches its output. So from path A to, so from source A to sum, the maximum delay occurs for 5.422 nanoseconds, and the logic, it is divided into two phases. For logic conversion it takes 3.998 nanoseconds, and for routing this will take 1.424 nanoseconds. Right. So next we will see the RTL view, register transfer logic, how it is being mapped in the uh, IC. So for converting this Boolean expression, it utilizes two AND gate and a three input OR gate. So the sum is realized using this multiplexer, and the cout is realized using this AND and OR gate. And you can also view the technology schematic also. And so here you can see the lookup table conversions. So on click on this, you can see the schematic diagram for C out, its corresponding Boolean expression, how it is converted through truth table, and its corresponding K-map. And similarly, you can view the outputs of sum also. So this is the sum output. So A XOR B XOR C. So C in, which is this Boolean expression, and its truth table, Carnot map. Okay, so the last stage we are going to do the implementation design. So in the implementation design, the routing causes and its corresponding binary bit files will be generated, and this bit file is dumped into the required Spartan FPGA device. So that's all about the design flow. Thank you for watching.